What if the key to perfect, unbreakable secrecy wasn't some crazy complex algorithm, but something much, much simpler? In this explainer, we're going to explore the deep and pretty surprising connection between pure randomness and keeping a secret absolutely safe.
All right, to get started, I've got a little test for you. We're going to see just how good your intuition is when it comes to randomness. Picture this: 2 rooms. In one, someone's flipping a light switch based on a real coin toss. Heads on, tails off. In the other room, someone's just making it up, trying to look random. The big question is, can you tell which one's the fake just by looking at the results?
Okay, so here are the 2 sequences. Room A, that's the person just winging it. Room B is from the actual coin flips. Now take a second. They both look pretty random, don't they? You've got a good mix of ones and zeros in both.
So how in the world are you supposed to spot the fake? Well, the secret isn't about looking for some obvious repeating pattern and just counting the ones and zeros. Nope, that's not going to cut it.
This all comes down to something called the frequency stability property. It sounds fancy, but the idea is simple. In a truly random sequence, any little chunk, say 3 flips in a row, is just as likely to happen as any other. So, heads, heads, heads is just as probable as heads, tails, heads. Our brains have a really hard time with that idea.
And this is where the fake just falls apart. If we graph the real coin flips, you'd see all the little 3-digit sequences showing up about the same amount of time. A nice flat line. But look at the human's attempt. It's all over the place. We just can't help ourselves. We think a long string of ones doesn't feel random, so we avoid it. Our bias is a dead giveaway. The forgery is, well, it's totally obvious once you know what to look for.
So, okay, fun little puzzle. But what does this have to do with secret codes? Well, it turns out this isn't just a party trick. It's everything.
Because when you think about it, what's a codebreaker really doing? They're hunting for those exact same biases. They're looking for predictable patterns. Anytime a cipher isn't truly random, it creates a pattern, and that pattern leaks information.
This leads to a really cool metaphor, the fingerprint of a language. Every language has one, right? In English, E is everywhere. Z is pretty rare. The first simple ciphers, they failed miserably because they didn't hide this fingerprint at all. So the whole game becomes, how do you disguise your fingerprint?
For hundreds of years, this was the central problem. And one of the most clever attempts to solve it was something called the Polyalphabetic Cipher. The whole goal was to flatten that fingerprint, to smudge it so it couldn't be read.
So here's the gist of how it works. Instead of just shifting every letter by, say, 3 spots, you pick a secret key word, like key. You turn that into numbers. K is 11, E is 5, Y is 25. Then you just repeat that sequence of shifts, 11, 5, 25, 11, 5, 25, all the way down your message. It's like having a whole bunch of different simple ciphers that you cycle through.
But there's a fatal flaw. You see it, right? The key repeats, and repetition is the absolute enemy of good cryptography. That repeating pattern, even though it's more complex, is still a pattern. It's a partial fingerprint that a smart codebreaker can latch onto.
So if you're a codebreaker, let's call you Eve. Your first job is to figure out how long that repeating key is. You could check the letter frequencies of, say, every 3rd letter in the message, then every 4th, then every 5th. As soon as you guess the right length, bam, that familiar lopsided fingerprint of English suddenly reappears. And from there, you're not breaking one complex code anymore, you're just solving a handful of really simple ones.
So this was the problem for over 400 years. How do you completely, totally erase that fingerprint? How do you create something with no leaks? Well, that brings us to the holy grail, the unbreakable code, the one-time pad.
And the answer, the one magic ingredient they were missing all along, was the very thing we started with. Perfect, pure, unadulterated randomness. Not the fake stuff from our heads, but the real deal.
The rules for the one-time pad are beautifully simple. First, your key is in a word. It's a list of truly random numbers, or shifts. Second, that key has to be just as long as your message. No repeating. And third, this is the big one. You use the key once and only once. Then you destroy it.
And the result of following those rules? You get a perfectly flat, perfectly uniform frequency distribution. There are absolutely no patterns, no statistical clues, no fingerprint for a codebreaker to find. It is quite literally, mathematically impossible to break. This is the real deal. It's the kind of security that was used for the Moscow-Washington hotline during the Cold War.
Now, to really feel how powerful this is, you have to get a sense of the sheer scale of what's happening. We're talking about something called a combinatorial explosion.
Let's just put this into perspective. Say you want to encrypt a 5-letter name using one of those old, simple ciphers. Okay, there are only 26 possible ways to do it. You could brute force that in a few minutes. But with a one-time pad? Well, each of those 5 letters gets its own independent random shift from 1 to 26.
So the number of possible encrypted messages isn't 26. Oh no, it's 26 times 26 times 26, 5 times. That gives you almost 12 million possible ways your 5-letter name could be encrypted.
12 million is a huge number, but it's still kind of abstract, right? So let's make it real. If you printed out every single one of those possibilities on its own sheet of paper and stacked them up, that stack of paper would be over a kilometer high, a whole kilometer of possibilities.
And that is perfect secrecy. The codebreaker grabs your encrypted message. What they're holding is just one single page from that kilometer-high stack. And here's the kicker. Because the key was truly random, every single page in that stack is an equally likely answer. They have absolutely no way of knowing if the original message was apple or zebra or hello. It's perfectly secure.
So there you have it. The secret to perfect security isn't some ridiculously complicated machine. It's found in the simple, elegant, and profound nature of true randomness. Which just leaves us with one final big question. If perfect randomness can create perfect security, what else out there could it unlock?